Rule number 7, the chain rule. This is the derivative of a composite function. What happens when you have a function inside of a function? And this is connected to the foreshadowing that I said here. Initially in this question, you have 4t squared minus 1, which is one function, inside of being squared. So we have a function inside of another function. Now we did this one by multiplying it out so we could get to rules that we knew how to do and found the derivative. But the question is, if we had a bigger number like 7, it would not be fun to multiply out. Not impossible, but not fun. Is there a shorter way that we could do this instead of multiplying it all out? The answer in rule number 7 is most likely yes. There is a shorter way. So here, what would happen if you had x plus 2 all cubed and you wanted to find the derivative? And then it says write your answer in factorized or factored form. So what we do is we multiply it all out. Here I used the binomial theorem. X plus 2 times x plus 2 times x plus 2. Simplified it to get 4 terms, right? Does it make sense that if you have something to the power of 3, that in the binomial expansion you should get 4 terms? I wrote those numbers in green to remind you that those came from Pascal's triangle. I love it when we have a math question that reminds us of math that we've done in the past, and then we get to do that math again. Shake your head. You don't like that? Just give me new math that's easy. Don't have to use any knowledge of what I had before. There's a few exemptions. I'll allow you to use my 10 times table and adding. Other than that, I don't want anything. Don't bring up the discriminant or binomial theorem or anything like that. Whatever you do, don't say conditional probability. Okay. So once it's simplified, the derivative is easy, but now it says, can you write your answer in factored form? So I could factor out a 3, and then it just becomes 3x plus 2 squared. Now someone did this, and they looked at this, and they looked at this, and said, hey, maybe I could find a shortcut. Wouldn't that be nice? And anybody think they've come up with a nice shortcut here? Yeah, just the 3 came out in front, kept the inside the same, and subtracted 1 from the exponent. So then you said, well, does that always work? And you tried another one, x plus 7 to the 100. And you did all that work and factored it and found out that if y was equal to this, then the derivative of that one happened to be that. And you're like, nice. Okay? But then you go back and say, let's look at this one again. Is the derivative of this one equal to 2? Because that would be the pattern, right? Right? And if I multiply this out, I would get 8t squared minus 2. Ready to relook at our answer? Yeah. It didn't quite work. In fact, let's factor this and see what we could take out as 16t, leaving us with 4t squared minus 1. So something went wrong with this and this. In fact, I could almost make it look right. Can you see that I could have, take a 2 out of there, but then I have an extra 8t that can't be explained yet. Okay? So you're okay with me, my math rearranging here? That the answer that I wanted to get was 2 times 4t squared minus 1. And the actual answer had a 16t instead of a 2. So I made it a 2 and just noticed there was an extra 8t that couldn't be explained. Okay? So just for fun, I went and did a whole bunch of them by hand and got all the answers to what we kind of wanted, but then found out, right, there was this extra every single time. Are you okay with this as me saying this is what we kind of wanted? Just bring the 5 out in front, subtract 1 from the exponent. But in this case, we have an extra 2 that isn't explained yet. The next one, yes, I wanted that 40 to come out in front. I expanded this, got all 41 terms, did the derivative, factored it beautifully, and I got this, but I have an extra 6x. This next one, I got what I wanted, but I had an extra 4x cubed minus 1. And the last one, I got what I wanted, bring the 2 out in front, subtract 1 from the exponent, but I had an extra 5x to the 4. Whew. So I'm going to underline the extra part in blue. The regular, would you agree that underlined in green we could describe as our regular power rule? Just bring the number in front, subtract 1 from the exponent. That's our regular power rule. How do we explain the extra? So we're saying that the blue is just the derivative of the inside. So the inside function is 2x plus 3. The derivative of that is 2. Inside function 3x squared minus 7. Derivative would be 6x. Let's just check if it works for each one. Yes. Derivative of x to the 5 plus 2, 5x to the 4. So how do we, this is the chain rule. How do we describe it? Well, what we did first, which is underlined in green, I'm going to describe as the derivative of the outside function. The outside function here is to the power of 5. How do you do the derivative of something to the power of 5? Power rule says bring the 5 out in front, subtract 1 from the exponent. Can you see that that's what's done every single time in the green? And I'll describe that as the derivative of the outside function. And then the part that's underlined in blue, that's the derivative of the inside function. So whatever function is inside, you get the derivative of that afterwards. So the key to the chain rule is, can you see what's the function on the outside and what's the function on the inside? Because you do the derivative of the outside function first and keep the inside the same. Notice the inside didn't change in the first part in the green. You just keep the inside the same. Just do your derivative rule for the outside function. and then you multiply by the derivative of the inside function. This is the chain rule, and it can cause your brain to go a little bit crazy sometimes. Notation-wise, this is what notation of the chain rule says. Okay? In Leibniz notation, we do the derivative of the outside function multiplied by the derivative of the inside function. Not easy to see in the notation. Derivative of the outside function, and these are the words I'm always going to say, so I'm going to say it write it out here for you. We always do the derivative of the outside function and keep the inside the same, and then multiply by the derivative of the inside function. Again, in this particular one, the notation isn't necessarily easy to see. Okay? I think it's easier to see in Newton's notation. The derivative of the outside function, keep the inside the same, multiplied by the derivative of the inside function.